but didn't do astrophysics mainstream.
Yeah, okay, yeah. Bhanudas was not an astrophysicist per se.
Sir, we are live.
Yeah.
Okay. Good evening to all. On behalf of Indian Physics Association, Roorkee chapter, and Physics and Astronomy Club and Department of Physics, IIT Roorkee, I welcome you in this lecture series, Astro with ARIES. So this is the second talk in this series and will be delivered by Dr. Indranil Chattopadhyay. So now I request Professor Nataraj to introduce the speaker.
It's my pleasure to introduce Dr. Indranil Chattopadhyay. He hails from West Bengal, and Professor Chattopadhyay did his BSc and MSc from University of Kolkata and PhD from S.N. Bose Science Center in association also with Jadavpur University. And he completed his PhD in 2002. Later on, he moved to Catholic University of Leuven in Belgium, and there he spent around 2 years. As a second postdoc, he took Chungnam National University in South Korea. There he spent about 3 years. Okay, so later on, he had a brief stint at S.N. Bose Center for about 2 months or so before joining Aryabhatta Research Institute, that is called ARIES, in Nainital. Back in 2007. Ever since then, so Dr. Chattopadhyay is associated with ARIES. And Dr. Chattopadhyay's main research interests are actually on hydrodynamics and magnetohydrodynamics. I mean, in the environments of compact objects, particularly that of black holes and neutron stars. Dr. Chattopadhyay is also interested in the study of gamma ray bursts and also extragalactic jets. So he has actively been involved for over a decade in teaching, particularly for masters and pre-PhD students. And he teaches mainly the courses related to plasma physics, hydrodynamics, and magnetohydrodynamics in also the relativistic environments, and its applications towards, as I said earlier, the astronomy and the compact objects in particular. He has taught several courses on general relativity and also related to cosmology. And Professor Chattopadhyay, he has plenty of project and research students. He has already awarded 1 PhD, and several PhD students are pursuing their research under him. He has held several academic responsibilities at ARIES. He was the chairman of academic committee for over 6 years, and he is also the chairman currently for the science committee, which proposes scientific proposals and problems for a 3.6 meter telescope at ARIES. He has organized conferences, particularly that related to recent trends in the study of compact objects and the theory and observations related to it. Dr. Chattopadhyay also has written articles in one of the most popular Bengali dailies called the Anand Bazar Patrika. And today's topic is actually related to black hole singularity and the stellar motion around it. As you all know, it is very much related to 2020's Nobel Prize in Physics. Half of the prize went to Roger Penrose for the discovery that black holes could be formed because, I mean, due to the prediction of general relativity, and other half jointly was awarded to Reinhard Genzel and Adria Ghez for the discovery of supermassive compact objects that is hosted at the center of our own galaxy. So without much ado, I request Dr. Chattopadhyay to take over. Thank you.
Thank you very much, Nataraj and Sumanto, for this, first of all, for these kind words, and also to invite me to give this lecture. So once it was announced, so there's some people in ARIES itself asked me to give a lecture, but I was actually at the time giving course on fluid mechanics. I said I don't want to disturb that, so maybe when I start my GTR course and cosmology course, then I can give it. It will be much better for me to give it talk like that. But I haven't finished my fluid mechanics course as well as yet. So The point is that it is a little bit early now for me, but anyway, that's very. So it is giving me an early preparation for the special course I will be giving on this to the ARIES students. Thank you very much for that as well. Okay, so we'll be talking about black hole singularity and stellar motion around it. Okay, so this year's physics Nobel Prize is hogged by black hole physicists. Roger Penrose a bit belated. Andrea Ghez and Reinhard Genzel, they are still in their prime, not way past their prime. Penrose is an old man now, about 90 years old. And Roger Penrose is a person who visits India a lot. Sumanto, you can do one thing. You can just, you know, my video, you can just turn it off. I'm just, because that would save a lot of bandwidth. But anyway, it doesn't matter. So, so here is a picture here of M87 black hole, the center of the M87 galaxy. I would say that the black hole, this preponderance of Nobel Committee towards black hole is somewhat has been guided or sort of shepherded by this picture that was taken by the Event Horizon Telescope, just showing that indeed there is a hole at the center of the M87 galaxy. This team is not fortunate enough to take another picture. They also tried to do that for our center of galaxy, that is the Milky Way, but they are not being able to do it because the matter falling into our center of galaxy is very weak. So the signals are quite weak. So, but anyway, so let's start our discussion today. Okay, so we know what are black holes. Black holes are we know there are three types of dead bodies of stars. The lighter stars ends up white dwarfs, like our sun would eventually end up as a white dwarf. Heavier stars end up as neutron stars, and still heavier stars end up as black holes. So we know that any stellar structure is in hydrostatic equilibrium. And once the nuclear fuel it runs out of nuclear fuel, then it cannot, then normal pressure cannot hold on to the gravitation, the self-gravity of the stars. So they collapse. Okay, and lighter stars ends up white dwarf because their gravity is a little weaker, so electron degeneracy pressure is able to hold them. Still heavier stars whose gravity is stronger, they need a little bit strong effect, so the neutron degeneracy pressure sort of can hold it. But beyond a certain limit, so that limit is again a bit of a gray area. What is the limit of below which mass limit below which neutron stars form and above which black holes form? That is still not known. Okay. But we know that black holes do exist. There are lots and lots of indirect evidences. For our last 20 years or so, we are mounting evidence after evidence that black holes do exist. Although the journey of black hole was not that smooth, okay, the acceptance came much later. And there are many black holes in our galaxies. These are called stellar mass black holes, which is around few solar mass to tens of solar mass. But at the center of our galaxy, we also have a supermassive black hole, which is around 4 point something million, 4.5 or something million times the mass of the sun. Most galaxies, probably all galaxies, harbor black holes at the center, and probably they are formed during the galaxy itself. So, but that again, how supermassive black holes form, which are about million to billion times as heavy as sun, that theory is also is not very well rounded off. There are many theories, many suggestions, but no consensus as yet. All right, so physics around black holes cannot be described by your simple laws, but one needs the help of general relativity. And we know that Einstein proposed general relativity. And probably that's why he's called a genius. So the way he saw gravity, the way he could describe gravity is a pure genius. And he proposed the first part of his relativity in 1905, which is the special relativity. First, he proposed the general relativity, or the description of gravity in terms of relativity. And so now we have two aspects here. One is the relativity, the other is gravity. So let us try to understand both in simple terms to have a workable grip on general relativity. Okay. Okay, so we start with gravity first, and then we will move to relativity, and then we can sort of merge it later on. So gravity means Newton's gravity. That's what we knew. This formulation of gravity was a result of many astronomical observations of planetary motions around sun, as well as moon's motion around Earth. And that famous story about that apple falling onto Newton's head and Newton discovering gravity, it is essentially what Newton realized is that motion of moon around Earth, or motion of sun, Earth around sun, is exactly the same force that is making the apple fall onto his head. So that means that the moon is moving around the sun in a rotation, right? So therefore it has a rotational motion, or so rotational motion means it has the centripetal force, and that centripetal force is being supplied by Earth's gravity. So as apple is also falling under Earth's gravity, moon is also falling in, under Earth's gravity, except that it has an initial velocity in a direction such that it has put it into an orbit. So he used the Kepler's law, the third law specifically, that T squared is proportional to R cube, into the centripetal force expression, and with that he obtained the Newtonian form of the Newtonian gravity, the 1 by R square form of the Newtonian gravity. And if you remember our graduate courses, our BSc days, bachelor days, then we remember that the effective potential in Newtonian gravity is basically 1 minus 1 by R, which is the gravity. I put G equals to M equals to 1 in some unit system, plus L squared by 2R cubed, L being the specific angular momentum of that object that is going around. So this is called the effective potential. I think you remember that. This is, I mean, by the way, the talk will be mostly directed towards the students. So experts might forgive me for being a little too simple-minded. Okay, so yes. Okay, so Newton's. So this is the plot of that effective potential. Okay, so what we saw here is that there are minimas, which are the location of the circular orbits, and if the energy of the particle orbiting, the test particle orbiting the central star is somewhere here, then it will be an elliptical orbit. Okay, with this being the what should I say? Not the perigee. It should be perigee for if the central object is Earth, or perihelion if it is the central object is Sun. It will be periastron or something like that. Okay, so and this would be the apple, and so this will be elliptical orbit. If it is If it is 0, it will be, if the energy is the rest is equal to the rest mass of the particle, rest mass energy of the particle, then it will be an parabolic, and it will be hyperbolic if it is greater than the rest mass energy, or both of them would be like the unbound states. So we know that, right? This is well known. And with this new description of gravity, planetary motion, Earth's motion around, sun's, moon's motion around Earth, and other satellites, these are quite well explained. There was no problem with Newton's gravity, Newton's description of gravity. So, but there were two problems. First problem was, in Newton's mechanics, the force is proportional to the mass. Sorry, the force is proportional to the rate of change of momentum, or in other words, it's proportional to the acceleration. And the constant of acceleration, constant of proportionality is the inertial mass. Newton's gravity, on the other hand, when the gravity is uniform, is proportional to the mass. And the constant of proportionality is the acceleration. Okay. Therefore, there is no reason why the inertial mass has to be equal to the gravitational mass. But experiment after experiment, we find that the inertial mass is actually equal to the gravitational mass of the object. Why? It should not be so. Why is it so? Newton's gravity is, again, the second problem is the Newton's gravity is instantaneous, and it contradicts special theory of relativity, which was proposed by Einstein in 1905. And the third problem is the perihelion shift of Mercury, although Einstein was not too much bothered about the perihelion shift. So now let us discuss what is special theory of relativity. Special theory of relativity, in a nutshell, is about the measurement of position and time of occurrence of any event by different observers, or more specifically, observers who have relative motion, are in relative motion to each other. For example, if I am running after a car, then the speed of the car, if I measure it to be u, the way I have done it. So if my speed with respect to some bystander is v, and the car speed is u, then according to me, the car is moving away with a speed of u minus v. That's what we know, right? But there is an assumption here. The assumption is that the information that takes the light, which gives the information of the car to be in such a position in such a time, that information takes no time to reach either myself or the bystander. Or in other words, the information travels with infinite speed. Okay, so that's the assumption here. But we also know that another cornerstone of physics, which was Maxwell's equation, and it turns out that Maxwell's equation can be modified in the form of a wave equation, and that wave equation is essentially is light. Okay, the light wave, right? And the EM wave equation do not follow the transformation, which is actually the transformation we described. It's called the Galilean transformation. It does not follow that transformation. The Maxwell's equations, the wave equation from the Maxwell's equation, we get the speed of that wave, it turns out to be speed of light. But in Maxwell's equation, it is not mentioned. Probably Maxwell didn't even think about it. It was not mentioned that what happens if someone is moving with respect to the reference frame which is emitting the light. But it is coming out to be that always it is coming out to be the speed of light. Or in other words, Maxwell equation already contains the germ of special relativity. And taking a clue from this, it's not entirely clear what made Einstein to give this postulate. Probably he was more influenced by Maxwell's equations, or the fact that the Maxwell's equations can be manipulated to give a wave equation where the speed always comes up to the speed of light. Probably that. But taking a clue from that, Einstein postulated or added with the already relativity principle, that is the Galilean, what Galileo actually propounded, that that all laws of physics are invariant in inertial frames. To that, Einstein added that nothing can move faster than the speed of light, and the speed of light in vacuum is a fundamental constant. The consequences of that is that if the speed of light is constant, universal constant, then time and space intervals separately are not invariant. Rather, a space-time interval is invariant. So it can be proved quite more or less easily that if the speed of light is constant, then this ds is invariant for various observers. And both space and time coordinates transforms, like between various frames of reference following, and this transformation is essentially called the Lorentz transformation. And no physical information can move faster than the speed of light. Now, consequently, the velocity addition law between myself and the car changes from u minus v to u minus v by 1 minus v uv by c squared, right? And that means no physical information can travel with infinite speed. Therefore, Newtonian gravity violates special relativity. Now, Minkowski developed a space-time representation of events. I'm just referring it, just because we might want to understand that when we talk about GR. So he represented these events, special relativity, through space-time diagram, and it could be from the space-time diagram. If speed of light is constant, then Lorentz transformation can be derived, and all the length contraction and the time dilation can be easily found out through these figures. The one point here is that if respect to this, something is moving, then that trajectory is called a wire line. But in the frame of that, the rest frame of that moving observer, the wire line is actually his time axis. Okay? So that's what I'd like to say. So the two things to actually conclude, that forward velocity is tangent or the direction, instantaneous direction of the wire line or the trajectory in space-time, and that my time axis is actually my wire line. Okay, so with respect to someone else. Okay, the two takeaways from special relativity. Now let us discuss what is GR, and before we do that, some peculiarities of gravitational interaction was already noticed by many scientists, most notably by Galileo. And what he observed was that from his famous experiment from Leaning Tower of Pisa, is that whether it's a heavy object or a lighter object, both of them fall at the same rate. Or in other words, in a small region, in a small region, the acceleration due to gravity is constant. Okay, in a limited region. Okay, so say for example in a room in Earth. Now here comes a Gedanken experiment by Einstein, that if I and that same apple, let's say this is I myself and this is an apple, we have to imagine this is an apple. But anyway, so if we are sitting in a lift which is constantly accelerating up with the acceleration g, and we are not looking outside, then there is no way to tell that whether, because then I will be feeling also that so-called pseudo force, how we will sort of describe it. I will also feel an acceleration downwards, as would the apple here. So there's no way to tell whether I'm sitting in a room and under my feet there is a massive object with a gravity such that it is there is a acceleration due to gravity will be g, or I'm sitting in an a lift, accelerating lift upward, which is moving upward with an acceleration g. There is no way. Okay. What it means is that there is no difference between uniform gravity or uniform acceleration. Therefore, like pseudo force, it can be removed by frame transformation. So we feel weightless when we fall down, right? So, so that's the example of it. But if you accept that there is no difference between moving, I mean, accelerating lift upward and a uniform gravity downward, then we can use this lift to discuss something else. So if a lift is static and I shine say a laser, then the laser will go in a trajectory parallel to the floor, right? So it will just hit their B. So we'll say that light travels in straight line. If it is moving with constant acceleration, then also it will not hit B, assuming that the speed is comparable to the speed of light. It will not hit at B, but it will hit at B prime. But B and B prime would be connected by a straight line. However, if it is accelerating, then it will be traveling up with half gt squared. In time t, it will cover a height of half gt squared. And if you actually calculate the position of the trajectory of the photons that are coming, the laser photons, it will actually be a curved line. Half gt squared will be something like a parabola. So from this, Einstein understood that the space-time in gravitational field is curved. However, there's the third observation about gravity. Although if from the leaning tower of Pisa, if I actually drop to, I mean, if I take two poles and I drop a heavy ball and a lighter ball, they will be falling with the same g or the same acceleration. And someone sitting over this small ball will not see the heavier ball to be moving at all. If he just sees that ball itself, nothing else. But if I take these two poles at a larger distance, then the larger ball, the smaller ball and the larger ball, they will see each other coming towards each other, right? And they will collide if they are allowed to fall up to the center of Earth. So that means locally, these freely falling objects are uniform inertial observers, but globally they are not. If at a larger distance you put it, then they are no more inertial observer, because initially they were static, and as they fall, this fellow will see that this guy is coming towards it, and this guy will see that this guy is coming towards it, and therefore they are not inertial observer. So the conclusion of these, if you conclude all these things, is called the principle of equivalence, or this is the cornerstone of general theory of relativity. That is, uniformly accelerating frame is equivalent to uniform gravitational field. Or locally, more generally, locally gravitational field vanishes. But locally, the space-time is flat. Okay. So from the second observation, Einstein concluded that gravity, the expression of gravity is curvature of space-time, and that locally it can be sort of transformed away, but globally it cannot be. You cannot have a single inertial frame which can replace gravity globally. Here that gravity bends space-time, locally one can construct a reference frame where the curvature is transformed away, but one cannot construct a single inertial frame to replace them. So therefore, Einstein had to give the description of gravity, and it has to be in a gravitational field. It is not a force equation. So Einstein did not generalize Newton's law of gravity. Rather, he generalized the Poisson equation, because Poisson equation, even it's Newtonian gravity, but it is actually giving a field, a gravitational field. Okay, so Einstein's famous field equation is actually a generalization of the Poisson equation for relativistic gravity. Okay, so that's the famous Einstein equation, field equation, and it is essentially a generalization of this Poisson equation. Here, the del squared phi is the gravitational potential, Newtonian gravitational potential. So del squared phi is essentially this. Okay, so this is the Ricci tensor, and this is the Ricci scalar. This R is Ricci scalar, and they are made up of double derivatives and single derivatives of the G mu nu. G mu nu are the metric tensors, which has the information of curvature and therefore of gravity. Okay, if the Riemann the Ricci scalar is 0, then the space-time is flat. Therefore, there is no gravity. If it is not 0, then there is curvature, and therefore there is a gravity. Okay, and so this is the field, and this is the source of the gravitational field, the T mu nu. It has to be pointed out here that general relativity is nonlinear, and the nonlinearity comes because the source, any source of matter is a source of gravity, whether it's angular momentum, whether it's temperature, heat. Any source of energy is a source of gravity. So that makes it definitely nonlinear. And this is one form of the Einstein field equation. This is another form, equivalent form of Einstein equation, where R mu nu can be expressed in terms of the T mu nu and the scalar, T mu nu scalar, or the trace. Okay, and one can solve these equations. If one solves this equation, they will actually retrieve the form of the various components of G mu nu. And therefore, once you can do that, you can write the line element or the metric tensor once the G mu nu is known. Okay, and it is not constant, as one can understand. Okay, so and one of the effect of this principle of equivalence is that one can replace the ordinary derivatives of vectors or tensors into covariant derivatives. Covariant derivatives are the generalization of derivatives in a curved space-time. Okay, I'm not going into details. Through a quantity called Christopher symbol, and they preserve the tensor properties. Okay, all right. So trajectories in curved space-time is the shortest possible distance, and for particles moving freely in gravitational field, these trajectories are called geodesics. All right, so Einstein never thought that his field equation would be solved, but soon after he published, Karl Schwarzschild, a German soldier, he actually solved this for Einstein's field equation for a spherical distribution of matter. Okay, and so this is the famous Schwarzschild line element or metric, and this is the GTT. And this is GRR, and these are all G theta, theta, and G phi phi. The four, it is a diagonal metric, so you have only 4 non-zero components, and they are diagonal. Now, this is for a star of radius of a mass m, and what will be its field or its line element at a distance r from it. Okay. Now, if I can collapse this mass into a distance which is less than 2 gm by c squared, Then at r equals to 2gm by c squared, which is called the Schwarzschild radii, or it's also called the horizon, the radius of the event horizon. This is rg, which we represent. So at r equals to rg, it can be shown that the matter crossing the horizon, it crosses with the speed of light. Okay, and therefore the escape speed also becomes the speed of light, and then nothing can escape from. If I can squeeze that entire matter within that Schwarzschild radius, okay, and such an object is called a black hole. It is initially called as a collapsar, but anyway, now it's called a black hole. Okay, but there is some interesting properties. Apart from at r equals to rg, one can see that at r equals to rg, gtt is 0, but this diverges. Okay, therefore the entire metric will diverge. At r greater than rg, gtt is negative, but grr is positive. But at r less than rg, it reverses. Gtt becomes positive and grr becomes negative. Another thing is that if we calculate the coordinate velocity, that is, if it is r, I mean, if I just calculate the dr dt, then at r equals to rg, dr dt goes to 0. Okay, so this is the expression of the dr dt for a spherically collapsing matter. However, it has also been shown in GR relativity, if you actually calculate the hydrostatic equilibrium for general relativity, that hydrostatic imbalance is not possible if I can squeeze the mass close to a region which is roughly around Rg. Okay, if you do that, then it is greater than 8 by 8. So it's basically like if I can squeeze it to a radius such that 2gm by r is greater than 8 by 9, then there is no hydrostatic equilibrium possible. At r equals to rg, it is 1. So if I can squeeze it up to very close to the gravitational radius or the Schwarzschild radius, then there is nowhere there in a hydrostatic equilibrium. It has to collapse. Okay, but from these facts, one can understand there's something funny going on at r equals to rg, and people were very, very wary about it. Okay. In 1937-38, one Indian, Vishweshwar Datta, published the first paper on gravitational collapse, and later, more famously, by Oppenheimer and his student Schneider. Okay, so that's the paper in Physical Review in 1939 by Oppenheimer and Schneider. I couldn't get a hold of Vishweshwar Datta's paper, so I'm sorry for that. But anyway, so what they said that, okay, if I calculate the coordinate velocity, then it will be collapsing with a coordinate velocity. If it collapses with the coordinate velocity, that's fine. That it is not collapsing at all. It will sort of, for a observer at infinity, it will seem that it has stopped collapsing. However, if you calculate that from a co-moving observer, then it's somewhere written here in the abstract itself, then it takes finite time to go from some finite r to r equals to 0, collapse to r equals to 0. Okay, so therefore it can actually fall in.
Hello.
Yeah, it seems there's a problem with this internet connections.
Okay. कांटेक्ट नहीं हो पा रहा है क्या लग रहा है?
Yeah, he is again logging in actually.
Okay.
Yes, Dr. Chattopadhyay. So please turn off your video so that it will be better. Yeah. Yes. Now we can share actually.
Okay. All right. So I mean, I don't know from yeah, you can see, right? So I don't know from where I just sort of got, I mean, disconnected. But the point was that Karl Schwarzschild actually found this line element. And in this line element, there was some problem. The problem was that R equal to RG is 2gm by c squared, this 2gm by c squared. There the ds or the line element blows up. That's number one. Speed of the escape speed at R equals to Rg is also the speed of light, and therefore it's called a black hole there. But interesting problems are that not just that. So there are other things that within R equals to Rg, the GTT becomes positive and GRR is negative, while outside R equals to Rg, GTT is itself negative and GRR is positive. You can see from here. So this is like GTT and this is GRR. And moreover, at R equals to Rg, the coordinate velocity goes to 0. Okay, this is the expression of coordinate velocity. You can put R equals to Rg, then it will become 0. Now, so therefore, it suggests that as the matter is falling in, then that matter will pile up near the horizon, I mean, or the R equals to Rg. However, it has also been shown by GR that hydrostatic balance is not possible if 2gm by R is greater than 8.9 and 2gm by Rg is actually 1. So if a star collapses to a radius close to R equals to Rg, then it has to bound to go in. It cannot sort of stay there. There's no hydrostatic equilibrium possible. But still, R equals to Rg, there's something funny going on. Okay. The first paper on gravitational collapse was by Vishweshwar Datta, and in 1937-39, but later more famously by Oppenheimer and Schneider in 1939. So they actually showed that if they showed it for dust, but anyway, they showed that if you are actually the co-moving observer, then the time taken from a star of radius r, finite radius r, to collapse it to an r equals to 0, that time taken is finite, not infinite. So a collapse is always possible. However, people remain skeptical and assume the assumption of dust and spherical symmetry may play a trick in these results. Okay, so people remain skeptical, and black holes were not, I mean, for astrophysics, holes were not very seductive topic to research on. But something happened in around 1955. A young Indian researcher, who basically is Amal Kumar Rai Chaudhary, was a college teacher then in 1955, was asking some interesting questions. The question is, gravity attracts, we know that, right? Then the trajectories of the particles in the gravitational field should draw closer to each other. The main departure from Rai Chaudhary's approach from others is that instead of trying to calculate single trajectories in a given static metric, Rai Chaudhary opted to study families of trajectories, bunch of trajectories together. Because in gravity, what do we know about gravity from GR? We know that the trajectory of the particle will come closer to each other. So the gravity in a curved space-time is measured by the relative distance of between the trajectories. Okay, so this is something like this. Let's consider a fluid flow. Let's say a river. Okay, it's coming from a small region and it is sort of spreading in a larger cross section. Okay, so that's how the let's say these are the streamlines of the flow of water. Okay, and this arrow is the local direction of the velocity. Okay, so we know that streamline, if I take the tangent to the streamline, it will give me the direction of the velocity. Now this expansion or contraction, that can be sort of measured quantitatively if we can find out the derivative of the velocity vectors, because that will give me how much it is getting, spread, or it is being constricted. Okay, so essentially expansion means that from a smaller volume, smaller cross section perpendicular to these local velocity vectors, you go to a larger cross section. Okay, if there is a contraction, then from a larger one you will go to a smaller one. So therefore so this is basically the expansion. Okay, so the derivative, or in more specifically, the divergence of velocity vectors gives you the quantitative measure of expansion or contraction. And this actually is called an expansion in relativity. The Relativistic use similar approach with the trajectories in curved space. So a bunch of trajectories in a curve. So that's what we know from GR, that matter curve space-time and curve space-time, and matter in free fall trajectories in gravitational field are called geodesics. And gravity attracts, therefore the trajectory should converge or focus. That's the term that people use. Okay. So the quantitative measure, as I said, is that of relative separation of adjacent trajectories as they evolve in the measure is the measure of gravity. Okay. So we have to take the covariant derivative of the four velocities. So in relativity, it makes no sense of talking about normal derivatives. We have to talk about covariant derivatives. Okay. So once the covariant derivative of the four velocity is separated or extracted into the trace, in the symmetric traceless term or the trace term and antisymmetric parts, we obtain what is called the Relativistic equation. This is given by this. Theta is called the expansion, or actually the four divergence of the four velocity. This sigma mu nu is the shear tensor. Okay, so it is the shearing of one component of the four velocities in a certain direction. So this mu semicolon nu and so on. Okay, and h mu nu is the projection tensor. So this projects any vector perpendicular to the four velocity. Okay, so if you actually do this, do a dot product of four u mu with the h mu nu, it will come out to be 0. So therefore, this tensor actually projects any vector or tensor perpendicular to the four velocity. Okay, and four velocity is the direction in which you are moving. Okay, and omega mu nu is the antisymmetric rotation. Okay, so that's the part. So if you separate it out, this is what we're going to get. And this term R mu nu is your Ricci tensor, the contracted Riemann tensor, and that contains the information of curvature. And so this term, this R mu nu u mu u nu, it essentially has to be positive always. That's a weak energy condition, they call it. And so it has to be because you see R mu nu can be expressed in terms of T mu nu, and T mu nu is the source. I mean, if I attach this geometric term into the Einstein equation, then it's the source of gravity, which is always positive. T mu nu is either energy or matter or mass, right? So it has to be positive. So this total term is of course negative because there's a negative sign there. So if one integrates this equation, okay, and so what Relativistic did was he assumed that the rotation to be 0. So then this you have the shear and only this term. Then you can take this up there and on the other side, and then if you integrate this d theta d lambda is by the way is the affine connection, affine parameter, or if you want to be only in GR and matter, then this lambda will basically be the tau or the proper time. Anyway, so this term, the sigma mu nu, this scalar sigma, and plus this one is always greater than 0 because that's what I just explained now. And in that case, if you integrate this equation, this d theta d lambda 1/3 theta squared, initially at initial time where theta is less than 0, then this shows that the expansion will remain 0. In fact, they will focus into a point. Okay, that's what gravity does. Okay? It brings separate points into a single point, and we have written for matter or time-like geodesics. But if you do it for photons or the null geodesics, we can also show it focuses. Okay, that's pure gravity, and that is the contribution of Relativistic. This Relativistic. So apart from Raychaudhury's work, two very important developments in science occurred. The first is the discovery of quasars, and number two is the solution of Einstein's field equation for rotating matter by Roy Kerr, also known as Kerr solution. And that also contains a physical singularity at its heart. Okay. So now this is, it has gone away from spherical symmetry. It is axisymmetric, not spherical symmetry. Still symmetric, but axisymmetric. So these two things actually was a big development for Roger Penrose to take. Okay, what are quasars? Quasars are point-like objects, extragalactic, and their spectra, the electromagnetic spectra is power law type, unlike stars. Stars have mostly a black body type spectra, and they have enormous luminosity. It varies, but it is enormous velocity. And only way to explain this is if there is a lot of matter falling into the this enormous black holes. Only then the radiation given out by this falling matter or accreting matter can explain the energetics. Okay, so black holes started to become very important after the discovery of quasars as well as the Kerr solution. So, but Kerr solution is also not general enough, right? Because it has these inherent symmetries, not spherical symmetry, but still has this inherent symmetry. So the question on collapsed object is still pertinent, that whether these symmetries help in forming the, artificially forming the singularity inside the horizon. So in 1965 paper, Roger Penrose raised this following question. So that's what he, I've taken it, I've just cut and pasted it from its abstract, that whether he wanted to find out that whether collapse without assumption of symmetry can also generate a singularity or not, or whether this formation of singularity is independent of any symmetry or not. That is the central question, and that is the most important part of this paper of 1965 by Roger Penrose. Okay, Penrose paper is deceptively short. It's only 2.5 pages. Okay, so this is the paper, and it is extremely highly technical. Okay, so it will be very difficult to give a colloquium on this. So we will discuss it qualitatively. The paper concludes that appearance of singularity is not an artifact of special symmetries in the solution, and the conditions encountered points to the existence of singularities, else contradiction will arise. Most notably, like Einstein's equation will not be valid, space-time, loses the meaning, emergence of local negative energies and so on, which we know that they are contradictory. So Penrose says that if we start, he starts with the argument that matter is about to collapse. It's just outside the horizon and has not crossed the horizon. Okay, outside the horizon, we know the solution, right? The solution is, let's say, if it is spherical collapse. So if the solution is the Schwarzschild metric, right? But once it crosses the horizon, what happens? That is the question Penrose raises. And Penrose, applying the Raychaudhury equation, finds out that the inward going null geodesics are the geodesics followed by the photons. Null geodesics intersects, which is same outside the horizon as well. But outgoing of geodesics, null geodesics, also meet. That is the expansion, that theta is negative for both outgoing and ingoing for null geodesics. That is a tremendous result, because what we found that null geodesics that's what we discussed, right? Just before that for if you start initially with negative theta, it will go and focus and intersect. But if it is diverging initially, it will not intersect. Okay, it will diverge, right? That's what Relativity equation says, outside the horizon. But inside the horizon, whatever you do, that it shows that both ingoing and outgoing geodesics, so this is an ingoing, so let's say this is the horizon. The ingoing null geodesics, they also focus. The outgoings, which we started with positive theta, they also come and converge, which means that there is, in other words, there exists a trapped surface within the horizon. Trapped surface is any closed surface where this will happen. That outgoing and ingoing both will be focusing each other. And Penrose concludes the existence of trapped surface is equivalent to the existence of singularity. Okay. So, for example, why he says that? Because if, say, you have these two geodesics which converges, right? Let us assume that so what Penrose says that the geodesic could just not converge here. They cease to exist. It is incomplete. You cannot go any further. So that means space-time loses its meaning inside the horizon. Okay. So how to prove it? So qualitatively, you can prove it this way, that we know that these geodesics are extrema points, right? So, but let's say it doesn't end here. Okay. Okay. By the way, geodesics outside the horizon can extend. They don't terminate. They don't end. Okay. We're talking about the inside the horizon. So if, let's say, we extend it, okay, then by definition, this is also an intrinsic extremum path. This is also an extremum path. So I can go from here and go like this. But I can also take a shorter path from here. If I just remove this kink, then I can just have another path here. So that is contradictory, right? So I said this is extremum, this is extremum. How come this also becomes an extremum? You cannot have, I mean, you know, a larger distance to be an extremum. I mean, two trajectories which they don't match, the size don't match, and they both are extremum. It cannot be, right? So this is contradictory. So this rather technical paper is considered as one of the greatest contributions in general relativity, and it showed that the singularity is a direct result of the general theory of relativity. So now that's what Roger Penrose did, but now black holes cannot be seen, so it has to be detected. Then you have to study observe the matter moving around in space-time around the black hole, and that's how the Andrea Ghez and Reinhardt, they got the Nobel Prize. Okay, so it's basically, if you write down the free fall equation, the freely falling equation, or the equation of free particle in a curved space-time in general relativity, this will be called the geodesic equation. So this P mu's are P nu lambdas are the four momenta. Okay, so if you do it for massive particles, that is not for massless particles, you can write this equation in this form. Okay, where S is the metric is the metric, or basically the proper time. Okay, so and E is the specific energy, L is the specific angular momentum. And here I have taken G equals to M equals to C equals to 1. So therefore, you don't have the G by C squared term here. Okay, and this part would behave as the effective potential. Okay, right. So if we look at this, this is our effective potential. If I plot this effective potential here with respect to R, then we can see, like the Newtonian potential, we have the minima. But unlike the Newtonian potential, for a given angular momentum, we also have extrema. The second point is that within a certain distance, okay, which is called the marginally stable orbit, you don't have minima. Therefore, your Keplerian orbits, or the orbits in which the elliptical or circular orbits, which are bound states, can only exist up to a certain point within which there will not be any Keplerian orbits. Okay, so and if you actually calculate the orbit, then it is very interesting that it will never come back to the same orbit. It will go like this. So, or in other words, the perihelion will shift a little. Okay. Because why is it so? Because if you expand this term, you will get one, which is the rest mass energy. Then you will have a 2r, which is the gravity, Newtonian type gravity. Then you will have L squared by R squared, which is basically the centripetal potential. However, there will be a third term, which will be 2gm by L squared by R cubed. This third term actually destroys the ellipticity of the orbits or the circularity of the orbits. So it will sort of this the elliptical orbits will start to precess. Okay, so that's what we're trying to say, that if it goes like start from red, they will go up to the blue and go like this, and eventually, if you give enough time, the entire apogee will go there on the other side. Okay, so that's what I say. Presence of R cubed term, 1 by R cubed term in effective, it gives rise to the perihelion shift, and that actually explains the perihelion shift of our Mercury. However, this is also true for the stars moving around a black hole, and that is exactly what Andrea Ghez and Reinhard Genzel, they studied for about 2 decades. They studied the stars in the vicinity of Sagittarius A star, which is our central black hole in our galaxy. Okay, which is around 4 point something 10 to the power 6 solar mass in mass. Okay, so they have studied all these stars. These are these various stars. This is actual image, and especially this star, this yellow orbit. Okay, this star is called S2. They have studied it, and this S2 has a closest approach of less than 20 billion kilometers from the central object, which is about around 1,000 Schwarzschild radius from the central black hole, and the velocity is measured is around 2.5% the speed of light, and the redshifts that are that obtain actually matches with the GR predictions very, very. Therefore, they put an additional confirmation of black hole environment in 2 energy bands, and is in optical and Reinhard Genzel in IR or infrared and sub-millimeter wavelengths. So the mysteries of the black holes and other compact objects. The mysteries of the black holes so this year's Nobel Prize actually sort of gave a recognition of Roger Penrose, who actually told us that the central singularity is a viable option. It was not understood before him that it is indeed a viable option. And India has some contribution here. We saw that Visheshwar Datta's paper, as well as Amal Kumar Raichud's contribution with this equation, which was used by Penrose for his singularity theorem, and later on also has been used by Hawking for the diverging, the Big Bang prediction. So, India also has this contribution, and along with, so it is so true for astrophysics that whatever theory you do, if you don't find observational or experimental verifications, it has no meaning. So conferring the prize to experimentalists or observers and the theoretician is really the greatest thing that they have done. Okay, so coming back to my work, so I've been asked to just to share a few words here. So the mysteries of black holes and other compact objects like neutron stars do not end with the Nobel Prize in 2020. So matter falling into these compact objects, if they actually come very close to it, they are the gravity is so strong that they are squeezed and pasted in the form of fluid and falls in the form of an accretion disk inside it. And the accretion disk gives a lots and lots of energy, and they are supposed to be they're called the prime mover in quasars and microquasars. And the spectra are mainly non-thermal. Even those from this region, powerful jets are seen to emanate. Okay? So why, if black holes are super attracted, why there is jets coming out? So that's a big mystery. So these are the things that I try to address. So for example, if you look at this is for stellar mass black holes, okay, Cygnus X1, one of the first poster boys of black holes. So Cygnus X1 generally are in two states, what is called the soft state, and another is called the hard state. In the hard state, the luminosities are lower. However, it is dominated by a power law distribution, while in the soft state, the thermal distribution, which is summation of black bodies, dominate. Okay, so and in the hard to hard intermediate states, highly relativistic jets are seen to emanate. Okay, during the soft state there are no jets, but in the hard state there are jets. So matter coming out very fast. Okay, this is SS433 with 26% the speed of light. Matter coming out with 26% speed of light. And this is MHE7, the newest poster boy for black holes, with that donut type shape picture that Event Horizon Telescope experiment took a couple of years back. And so this is, they have also a powerful jet with almost the speed of light, with jets emanating with the speed of light. Okay, so it's there in this multi-wavelength, it has been imaged. And also these power law photons in hard X-rays, they show some sort of a curious quasi-periodicity. Okay, why is this power law? I mean, if you do a FFT, fast Fourier transform of these photons, you see a spike. Why is it doing it? Evidently, the region that is generating these hard power law photons, they are oscillating, or they're in quasi-periodic oscillation. So one has to find out why this matter is, I mean, this plasma is doing these oscillations. There are no consensus about that. Okay, we have our theory, some other groups have some other theory, but there are none. Moreover, these jets, these quasi-periodic oscillations, the luminosity as well, they follow some sort of a hysteresis curve. Here it is the intensity versus the hardness ratio. The hardness ratio is the amount of hard power law photons, ratio of the hard power law photons with the soft thermal photons. You take a ratio, you find out what is called the hardness ratio. And if you do that, if you plot that with the intensity, one can see that it forms some sort of a Q-type diagram. This is also called the Q diagram. And during this process, observations, one can see that the jets, the QPOs, they evolve. Okay, so around here, the jet starts to form. The QPO is millihertz and very small. And then when it goes there, the jets become stronger and the QPOs become stronger. When it goes up to here, then you get the relativistic ejections as well as very high soft QPOs. And once this is done, it's finished. It goes to no QPO, no jet, and in the soft state. Okay, so that's how it evolves. So, so these are the things that need to be addressed. So our take is that what we do, we take the entire all the components of the equations. So basically, we solve fluid equations in presence of magnetic field or in absence of magnetic field in curve geometry. So these are the equations that will look like. UR is the radial component of the fold velocity. U phi is the azimuthal component of velocity, and so on. So we take all these equations and we try to solve them analytically sometimes, and most of the times numerically. Okay, and so these are details. So like, I mean, in curved geometry, cylinders, I mean, you don't have cylinders, you have what are called the von Zeupel surfaces, curved surfaces. So one has to solve, the jets are coming out, they'll be following one of these trajectories. So one has to solve this, how the jets, accreting matter is coming and actually following that as jets. So that one has to do. We have done that, but again, a lot of work needs to be done. So these are the simulations. We can numerically, we can actually match our analytical predictions pretty well. These are the published papers, and we can, if you do simulations, we see that bipolar outflows in the form of jets that are coming. But of course, forming the jet and accelerating them to the speed of light, close to the speed of light, is not easy. So, and again, these central regions which gives lots of hard radiations like hard X-rays and gamma rays. They also can show that they oscillate, and if you do an FFT, then the power density spectrum can show that there's an oscillation. So, and so these are the things I do. So basically, if we actually do these simulations, we actually solve for the flow, and then from there we calculate what are the radiations that are coming out. And those radiations, so this is some small calculations here, that if the radiation this is a black hole, and there is a radiation coming from here, you see the trajectory of the null geodesics will be like this, right? So it will sort of be curved. So as radiation that is coming from here can actually go out in this direction, so on. So, and this is the photon orbit here, the blue one. This is a black hole, and the others. These are these are escaping these trajectories, but not all of them. There are also some capture orbits. You can see that some of them are falling onto the black hole. So now the point is writing from these, one can actually calculate the photon trajectories coming from this accretion disk and reaching Earth, our satellites. Okay, so these are projects which are perfect for MSc students for 3-4 months or even 6 months. MSc thesis projects, fantastic projects. Okay, you take one object and we can do this, and then match with the observations. Then we are doing very good science. Nature paper are guaranteed for those. And there are also, but there are some deeper questions that the fluid mechanics or plasma physics of relativistic flow are not complete. I mean, there are lots of loopholes in those. The real nature of viscosity of how viscosity works in relativistic plasma is a big question. Okay, some stalwarts did, but nowadays almost no one does that. And then the energy exchange processes between electrons and positons is one thing we are doing with one of my PhD student who is about to submit her thesis. We did, and it's a very good work we did in it. So we actually proposed, used, these equations are essentially incomplete. So we used and give degenerate solutions. So we used the second law of thermodynamics to find out which is the correct solution. So we did that. But the point is that there are a lot of things to be done in studying the energy exchange processes between electrons and positive ions in plasma around black holes and neutron stars. And I'd like to collaborate with interested physics faculties on these topics. And I'd be very happy to collaborate with various engineering departments to, for example, with computer graduates and faculties. We can upgrade our codes for general researchers. For example, the codes we write is very technical. Okay, so if I give it to someone, that fellow has to know everything about the code as well as the physics and so on. But popular codes are those which are used like black box. We can be used like black boxes. Okay, so those expertise would definitely would welcome, which I don't have. Software, these things. I'm more. I mean, it's more about doing mathematics with computers, but not about user-friendly codes, general user-friendly codes. We can also, this is something, I'm just floating it like that. So there are some area where, which is called analog gravity, is that with fluids, we have fluid mechanics labs. With actual fluids, we can do some experiments, we'll mimic in the acoustic, not in the general relativistic sense, but in the acoustic level, we can mimic, wormholes, white holes, black holes, all sorts of things. Okay, so those things can be studied. There are some people who do it. It's very interesting, interesting topic of research. So the summary is that Roger Penrose was awarded for his tremendous contribution in physics and convincing the world that black holes are a viable solution. And Andrea Ghez and Reinhard Genzel, sorry, the spelling, there's a mistake. It's not Genzel, it's Genzel. But the perseverance to map the neighborhood of a massive black hole in our own galaxy for more than 2 decades. Thank you very much.
Okay, so we can accommodate a few questions. So I read the questions and I request Dr. Chattopadhyay to kindly answer it. Okay, so from students who asked why would replacing the sun with black hole could not attract the Earth to it?
Oh, yeah, that's very okay. I can go back to the Kepler problem, right? Oh, no. Was it there? Where is it? Oh, sorry, just a minute. Huh? Yeah. So you see, if sun is somewhere here, okay, we are in one of these orbits, okay. Let's say this is the angular momentum we have, whatever it is, right? But this is far away from the sun, okay. If we replace the sun with a black hole of the same mass, okay, so the size of the sun is like is 10 to the power 10 centimeter. Okay, yes, it's 10 to the power 10 centimeter, right? Okay, so that's the size of the sun, radius of the sun. If we make a black hole out of that, it will be just 3 kilometers. That means 3 into 10 to the power 5. Okay, 1 AU is around 10 to the power 13, I think. Yes, 10 to the power 13. Sorry, the sun's radius is around 10 to the power 11, 7 into 10 to the power 10 centimeters. Okay, so it's around 10 to the power 11. So around 200 sun's radius is 1 AU, right? So if we actually calculate the Schwarzschild radius, is thousands of Schwarzschild radius. At those distances, the Earth doesn't know whether the sun is general relativistic or special relativistic. Okay, the GR effect comes if you look at the metric. Okay, yes, this is the metric, right? The GR effect comes because of the compactness ratio, that is M by R. Okay, so you can have a very large M, but if the radius is also, the R is also very large, then it does not have enough compactness to bend the the space-time. Okay, got the point? So a star, which is, for example, sun, which is, which is around 1 solar mass, it is spread over 10 to the power 11 centimeters, right? So the gravitational intensity is very low. So it cannot really bend the space-time. Had Earth been much closer, then the GR effect would have been very important, because then, this perihelion shift will come into play. But at Earth's distance, it is almost Newtonian, even if you replace it with a black hole. Gravity is about this compactness ratio, M by R, how much mass you pack inside a small volume. Okay, if you put a lot of mass, for example, let's say our own galaxy, its mass is huge, massive mass, right? Billions of stars are there, right? So that much mass is spread over tens of kpc. So therefore, the mass that is being packed is being distributed. So it cannot affect the space-time around it, cannot bend the space-time around it effectively. So the gravity is weak. Okay. Does this answer the question?
Yeah, probably yes. There is another question. How do you differentiate between the photons coming from the accretion disk and the photons coming from the due to the gravitational lensing of other sources?
Oh, okay. All right. That is observers will make sure of that. That is, if you first of all you have to focus in that region. Okay, then you have to get rid of the foreground photons. Then you have to get rid of the background photons. You have to check what are the locations. Close by locations of the stars. Okay, nearby stars. Okay, so from the nearby stars, if you can see emission, and from that object you can see an emission line. If their redshifts are same or similar, then you will know that it's coming from those distances. Okay. There are n number of ways to do it. I just give you one simple example to locate the distance. I hope that answers it.
Okay, one last question, quite interesting. Can black hole shrink?
Yeah, according to Hawking, it does. So basically, I did not discuss anything about Hawking here. So it comes from Bekenstein's area theorem. But the problem is the black holes, what we see are astrophysical black holes. Then the rate of evaporation of black holes goes like 1 by m or 1 by mass. So so astrophysical black holes are very large. Okay, so and the evaporation rate is very, very low. Okay, there is no way of evaporating the physical black holes, the astrophysical black holes that we see. If during the formation of this of universe, if you can form small black holes, then they will be interesting. They will evaporate. Having said that, if you go through the paper by Stephen Hawking, I think it's 1974, probably. I'm just forgetting the year. So what he does, he takes this classical gravity, that is general relativity, and near the black hole, the curvature of causes the formation of, continuous formation of particles and antiparticles, and using that and using the Shannon's information theory, he finds out how much of those negative the antiparticles are eaten up by the black holes, and that way the black hole's energy is getting reduced and getting evaporated. So one of the criticism of that is that you are using classical gravity while using quantum physics of pair creation and particle antiparticle creation and particle creation processes. These two may not be compatible. Okay, so however, the problem is the solution to this is finding a viable quantum gravity theory. It is not there. Okay, so Hawking radiation might be problematic, but there is no way to prove whether it's problematic or not, because there is no proper quantum gravity theory at this moment. But if you go by Hawking's theory of Hawking radiation theory, if you just assume that Hawking did everything correctly, then at least the astrophysical black holes, which are at few solar mass to tens of solar mass to millions to billion solar mass black holes, those are not likely to be we can definitely say they will not evaporate, and we don't see the mass to decrease from observations.
All right. So on the behalf of the organizing team, I take this opportunity to put forward the vote of thanks and acknowledging the support in organizing this lecture series. So I thank Dr. Indranil Chattopadhyay for delivering such a nice talk in this series. And I thank Physics Astronomy Club team members, which comes under Student Technical Council, IIT Roorkee, for their support in organizing this lecture series. And I also thank Professor G.D. Verma, our head of the department and President, Indian Physics Association, Roorkee chapter, and the team members. And special thanks to Professor Gaurav Shetty for being instrumental in organizing this lecture series. And I also thank all the audience for attending this lecture series. Thank you and good night.
Yes, Shumanto, there was, I think, somebody wrote